Ever wonder what happens when you push that button to get on the elevator? Stick around, we're going to find out. Going down. Hi, I'm Brad Wilmot and welcome to the Geek Group. Today we're going to learn just how elevators work. We're here at a local apartment complex in Columbia, Missouri, where our elevator technician, who has asked not to be identified, is going to walk us through exactly how elevators work, inside and out. I apologize for the shaky camera in advance. We couldn't use a tripod or anything because of space. So follow along. Okay, we're going to start here. We're going to check out the machine room first. One of the things about this building that the elevator guys will talk about later is the machine room is down on the bottom floor instead of the top. I apologize for the noise. In fact, I'll replace it with music.
Kind of while since I opened this door.
This is what you're looking at. This is the controls. This is what basically makes the elevator go up and down. You have the relays that control it up and down, open and close the doors, give it preference whether it's going up or down for demand. It's like a really old computer. It's got all these contacts that send signals down and control bigger relays.
Hey, you saw that contactor, good chunk.
Right. Big contactors coming up. This set of contacts down here control the generator. It's a DC generator. It's actually controlled with an AC motor on this end. That's AC.
Okay, so this is what we call a rotary converter.
Basically, right.
AC motor.
Right. That's what
with a
gives it
DC generator.
Right. So basically, with our control over on this side, we take the AC. We have rectifiers that turn it to DC. We come back over here to the DC end, and we give the fields a DC current. And by turning the armature inside that, we've created a magnetic field. And now we're putting DC back out on these brushes right here.
And that is this DC 600 volt?
This is actually around probably 200 or
Okay.
so. So basically what it's going to do, the DC that comes out on these brushes is what controls our motor over there. That's what runs the elevator up and down. And what dictates that, based on whether you pick an up or a down relay, you change polarity, and that's what makes the motor rotate clockwise or counterclockwise. You're just like switching a magnet around.
So we've got the 200 volts or whatever coming from here. It comes up to one of these
Basically goes through the
contactors.
contacts, right.
And then
based on which one picks it, it changes polarity, and that makes the motor go up and down. The motor's also a DC motor, so whatever output voltage you're getting on the brushes on the generator, you're getting right here. And this is basically the same thing. We have a standing field voltage DC on this motor, which creates a magnetic field. And when you apply voltage to these brushes, it puts it on the armature, and that makes it turn. You'll have a opposite polarity. There's a braking mechanism here. This is what keeps the elevator sitting still. Before it can run, this has to energize and pick up. There's a DC coil inside this box right here. And it becomes a magnet also. Basically everything on this elevator is magnetic. I mean, if you can think about it like that, it's electromagnetic. So when this coil energizes, this is all metal right here, this armature core, it'll pick up. It actually sucks these things in and lifts this brake off so the elevator can then turn. And this is geared. It's a geared machine. So basically, as you're looking at it this way, this motor rotates this way.
yeah, I saw it was.
It's got a shaft that it's attached to on the machine. You can see the shaft right there. It runs through there, and it's got a worm gear on it. It's actually got a gear going this way, and then we've got a gear here, and those are meshed together. And when this turns this way, it then turns the gear that way and runs your elevator up and down. This is a unique elevator also because it's a basement set machine. A lot
Yeah, I
of
know
your gear
most of them are up in a
on the roof.
on the roof in a machine
Right.
room.
That makes the cabling configuration really interesting. That is the selector. What that is, basically, this carriage right here is a simulation of where the elevator is, positioning. That gives feedback back to the controller and tells the elevator when to stop.
So it looks like a
Each one of
corkscrew.
these, yeah, each one of these pie plates represents a floor. So this bottom pie plate is the basement, first floor, second floor, third floor, fourth floor, and fifth floor. And there's these ramps and they have different signals for leveling, slow down. It tells it if it can open the doors. It can't electrically open the doors unless it has a couple of these switches made up. So
That was something
I'll
else.
run it up one floor and you kind of see it how it works. This carriage will pick up, and when it approaches this floor, it's going to drop back and then it's going to ramp up on these pies.
Okay, I'm ready.
They're called pie plates. So,
Yeah, it looks like it just rolls up the screw there.
right.
And the thing is,
And the
I noticed
feedback
it's
is when
chain
you-
driven there too.
Right, exactly. This tape right here actually is connected to the elevator. This metal tape, and it comes around. And of course, they had to gear it, the ratio. The travel from this pie plate to this pie plate simulates the travel in the hoistway. So if this rise is 45 feet, let's say, they had to gear it down to ratio, you know, where this travel right here represents that 45 feet. So the positioning of these pie plates is really critical.
So that's how you adjust if it's not.
If it's not on level, really, we never move these pie plates. These pie plates always stay in place because these represent where the floor is. Typically, if you have a leveling problem, you have a switch that's getting worn.
Oh, okay.
The bottom of these switches right here have a little carbon tip on them.
And those
that'll
will wear down, yeah.
Right, they'll wear down. So that changes where the elevator stops. Also, the brushes on the generator, as they get shorter, you can change. It changes performance and compounding, and so I got to stay on top of that and change brushes. These relays over here simulate when someone pushes a button inside the elevator or on the outside. Each one it represents a call. So if somebody inside the elevator pushed the first floor or the basement, here's 1C. When they push that button inside the elevator, this relay is going to pick up. It's going to make up a contact. It's going to send a signal over to the controller that says I have down demand. Based on this selector position, it knew it needed to go down. So it's heading down.
There's a place you don't want to be standing when this is live.
That's kind of it here, really. The cables, that's something that's kind of interesting. There's actually 5 cables on here. Each cable individually is capable of holding the load.
That was something that I was going to say is, you know, a lot of people are going to be wondering what keeps these things from falling down and being like a movie where, you know,
Right, I'll show you that on
thing
top.
plunges 100 feet. And
Right, I'll show you. We'll get on top of it.
that
I'll
is,
show you.
those are what, half-inch steel?
This is 1/2 inch, right? They're 8 by 19. That means there's 8 of these strands in each one, and then 19 strands in each one of those lays. So it's wrapped around. 8 by 19. The more cables inside the individual strands, the more flexible it is, and we need nice flexible cable because they do a lot of bends around these shivs. But basically, one cable has a breaking strength of 20,000 pounds, give or take. It might be 15 on this one, 18. But so it's capable of holding the whole load by itself. The reason why we have 5 cables here is for traction. We need it because...
These elevators are traction driven mainly.
Correct. We rely on traction on this shiv. This shiv is grooved and has a shape to it to bite on these cables. And when it turns, we rely on traction to grab a hold of these cables and turn and move the elevator. So that's why there's 5. It gives you more surface area.
Now, is this a counterweighted?
It is. The counterweights, actually, I'll run it to the top, and if you point your camera right here, you'll see the counterweights come down. So the elevator's at the bottom now, the counterweights are at the top. So when the elevator gets to the top floor, you'll see the counterweights come down.
There we go.
The counterweights weigh about 40% more than the elevator does. Reason for that is if you have to account for the capacity
Kind
of
of
the
balance
elevator.
it out a little bit.
Right. So when we have a full load on the elevator then weighs more than the counterweight.
And we'll put a link to how all of this balancing and everything works right here. It's really cool actually how these work. You see this motor is, what is this, maybe a 50 horsepower motor? If that?
Actually, it might not be that high. It's actually 15.
This is a 15 horsepower motor that's moving 5,000 pounds.
Sure, right. It really doesn't require that because
Yeah, it doesn't. It doesn't require it, and it's a balancing act.
Right, exactly.
If that elevator is 40% full, which is an average, then you're right in. You're perfectly balanced. This thing only has to tip it one way or another. That does not take any horsepower at all.
Exactly. That's right.
If they didn't do it this way, you'd end up with a 500 horsepower motor.
We could turn it by hand if we had a crank on there. You know. Actually, the first elevators were hand driven.
Yeah. It's very interesting. I mean, this is what, 70s?
This is, yeah, late 60s, early 70s. This is, actually, I think that this is the print states 1964.
Well, the building was opened in 66, so I figured it was
They were
original.
probably installed in 64, 65. They took about a year to put these in, I bet.
Now I imagine this is all just
This is just
spare
parts,
tools
yeah, right,
and
the spare
parts and.
spare parts for the elevator.
Now, what kind of maintenance do these things require?
They require lubrication, contact changing.
You got
The cables
need to be checked for tension, I assume.
Exactly, tension to make sure they're equal. You want equal tension on them.
Yeah, you get the rails that the car rides on.
Right. These actually have roller guides or tires on them. So some elevators have slide guides where you have to actually lubricate the guide rail. This doesn't require lubrication because it has actual wheels. You have to make sure the gearbox has proper oil level in it. The worm actually sits about halfway up, the oil does, on the worm. And the worm actually picks up oil and brings it up onto the gear and lubricates it. You might be able to see the gear actually right through I have a clear plexiglass cover on this. You can actually see the gear turning there and carrying oil.
Oh, I see it.
That's important that gear is carrying oil.
Here's a little bit better.
That cord right there, that black wire, is what sends all the electrical signals to the elevator. Right there. That's a traveling cable. It travels with the elevator. It's a very flexible wire, but it actually comes all the way back to the controller here.
You think about how often these things are used, it's pretty amazing how well they work. Yeah, I'm gonna...
For being close to 50 years old.
Yeah, exactly. That's another thing. For being... Okay.
And that cable right there, the smaller cable, that's actually a 3/8 inch cable. That is what stops the elevator in case of emergency. That's the it goes up over a governor that's calibrated that monitors the speed of the elevator. And if it goes over speed, it has a jaw that bites on that cable, and it'll set safeties on the elevator and bite down on the rails here and stop the elevator.
I've seen the how that works on Wikipedia. We'll put a link to that there. That's actually pretty cool.
These elevators have spring buffers.
Is that what this thing
those
here
are spring
is?
buffers, so if the elevator goes past the floor, that's what they land on. The reason why these are spring, these elevators only travel 200 foot a minute. If they travel above 200 foot a minute, then you have oil buffers.
Like a big old cylinder with oil in it.
A piston, right?
Yep.
Sticking up, and that softens the flow.
Okay, now the car's at the top, so now
The elevator's close to the top. I have it parked where we can see on top of it, so that's the counterweight.
Okay, now what is this here? Is this just a guard?
That's a guard. That's required by code. If I'm working in the pit, that keeps me from
getting your hand sliced off.
Right. The counterweights are pretty quiet. I mean, when they're running, if you're running,
you might not hear it.
Right. Exactly. If I'm down there working or sweeping or. Each door is equipped with an electrical interlock, so if this outer door is open, the elevator cannot run. It's a mechanical and electrical interlock. There's a hook that mechanically locks it where you can't just walk up and open the door, so that in the movies is fiction.
Yeah.
You have to have a special key to open it, and also there's a contact on there that that allows the elevator to run. So if this outer door does not get closed, it will not run.
It tells the controller, hey, I'm not good here.
Right, and there's switches right there mounted on the counterweight rail. You see that? There's a cam or a ramp mounted on the back of the elevator. When it comes down, that first switch, it's kind of a backup slowdown. It tells it, hey, you're getting close to the bottom. You need to slow down.
You're coming up on the limit switch here.
Right, and then the bottom one down there is a direction that would make it stop.
That's the hard limit.
Right.
Okay, you went too far. Knock it off.
Quit. Right. Electrically, it would say stop. but you can also get a good look at the other side of the gear and the sheave. You can see where the ropes wrap around the sheave and go up the shaft. You can see where they're hitched to the counterweight. There's 5 shackles
Okay.
where they're hitched.
Don't know how well that'll come out, but we can fix that in post.
I can show you on top too. You'll see the hitch on top real good.
Now this here is just the rail.
Right. That's the guide rail.
And I see it goes all the way down, even past the springs.
Basically, when in an elevator installation, that's the first thing that goes in. The guide rails dictate location of everything.
Yeah, I'm shooting video with the elevator guy.
I guess you got my message.
We ran into each other just as I came in. Okay, time to edit that out.
Yeah. So basically, the guide rails are the first thing that go in on an installation. You get location. There's prints that come out for the elevator, and you get that placement. The main guide rails and the counterweight guide rails, they go in first because that dictates the location of everything else. Because there's certain clearances that are required between the guide rail and this main entrance. So when they go to install an elevator, that's one of the first things they do is put in the guide rails.
You put the rails in and you follow everything out from there.
Exactly. You stack the rails, get them in. A lot of times they use what they call as a false car if they have to. They actually put a mock elevator or whatever inside the shaft, and they run up and down and do the rest.
Just
and then
to
they
do measuring and things
right,
like
get
that.
the rest of the install in. So we can grab this elevator since it's right here, maybe. And it took off.
And I assume that since you just kind of pushed it shut, it did electrically.
Yeah, it'll also close on its own. That's required. Also, outer doors are self-closing. There's actually a mechanical spring on this door.
So even if something
If you walk
acts
away-
up,
right.
it will close.
The inner door is what drives it. The inner door actually has a motor on it.
Yeah.
And then this outer door just goes along for the ride. But at the very end, they have to separate from each other. So
And
this one
that's
has
what
to-
that little
Right.
latch thing there
Now
was.
it's latched, so if I don't use this key to pick it, I
It will
can't
not.
open it. This requires a special key to open it. It drops in and there's a latch.
Yeah, what's funny is when the fire department decides they want to open
They're
it
not
with an
good.
axe.
Yeah, they're not good. Here's the top. This is where we were talking about with the cables again. This is where the cables hitch. There's a plate underneath. This is what we call the crosshead. It's kind of one of the main structures of the
That
cab.
looks like it takes most of the load.
It does. There's about a 3/4 inch thick or inch thick steel plate underneath this. It spans across and it's bolted to the bottom side. And then there's holes drilled or milled in there for each shackle. And these are actually a wedge shackle. There's actually a wedge inside this, right here inside the shackle, that it's a wedge fit. The cable's actually pulled through. You actually wrap it around the wedge and then you pull it up inside the shackle. That's a newer type of shackle. It speeds up the cabling process.
And that ain't going nowhere.
No, it's wedged in there. Originally these had Babbitt poured. I don't know.
Yeah.
The cable actually just went straight down into the shackle. You had to break the end of the cable and each lay, and you'd bend them back and put them inside the shackle and actually pour Babbitt melted inside there. There's the same slow down switches for the top side that's coming up.
So high limit.
Right. And you can see what the cables have to do. When they go off the driver on this car was on that wall. So they come up, they go over a set of shivs up there and then down to the car. And then from the
if I
other
can
side
get
it goes
the
up and over
camera to
2 other sets.
read it. There we go. I tried to get the camera to catch that shiv there. That's a good sized chunk of metal.
There's the governor up there that we were talking about if it overspeeds.
This right here?
Right. That cable's going over, that 3/8 cable is going up and over that. And if it gets overspeed, it's got a set of jaws, weighted jaws that you calibrate with a spring. And the faster you go, the further out the weights go.
And if it goes out too far,
It goes
they
out
hit
too
the edge of that
Right, we hit the edge
sprocket
of
and that,
it bites a jaw down on that cable. And then what the cable will do, it actually pulls up right here on this side. It'll pull up right here. And when it does, it's attached to the elevator also with another type of shackle. That's actually a Babbitt shackle. And it'll pull up and it has a safety plank. The first thing it does when it actuates that, you can see this is the front side of that jaw. it'll trip this out. This is a safety circuit. If it kicks this out, it'll actually stop the elevator electrically. Now, if the elevator's out of control for some reason, it continues to go, then it would actually go ahead and mechanically set the safeties right after this switch.
So if something real bad happened, the cables broke or something like
If
that, it would go boom, boom.
Yeah, if all 5 cables broke, the counterweights are going to go bang. They're going to go down. Boom. The car will go about 15 feet maybe, and then it's going to stop. Bang. It's going to bite these safeties. It really doesn't take long for it to get over speed. We do drop tests when we have a full load on the elevator. What we do, we simulate it by picking the brake, and it'll take off going, and once you get it going, it doesn't take long for it to go full speed, or actually over speed in that case to trip the safeties.
Terminal velocity is about 120 miles an hour, and it doesn't take long to get 5,000 pounds of metal and people moving that fast. And these are 200 feet per minute is what
200
they're...
foot a minute.
And I guess the safety's probably set at what? 275 or something like that?
Right, yeah. That's the electrical trip, and I think the mechanical goes a little bit over 300, but this is a really old door motor. Actually, that's what I'm here to do today. I'm here to clean. I'm going to clean the top of the elevator. It gets really dirty.
Yeah, it looks a little gungy.
It gets a really dusty. This building is close. The elevator shaft is close to the laundry room. And
Yeah.
It sucks a lot of dust in.
Well, and the airflow in this building leaves
Right,
something
it really
to be
sucks
desired.
it. So, any residue of oil, because this is actually an oil pot door operator. This is what opens and closes the doors. At the final open and final close, it actually has 2 pots or 2 checks right here that are actually oil filled. So there's a piston inside here that when the door operator, when this arm pivots around, when the door opens, it'll actually slow it down. So when this arm actuates around inside here, it'll go into this pot and you can adjust this check right here and it'll slow the door down a little more at final open and close. It's also got a DC motor up here that drives it off the control down there. This box is full of switches and contacts that give it feedback to tell it where the door is located, so it knows to slow the door down and stop trying to close when it gets fully closed.
That way you don't burn something up.
Right, that way you don't burn your motor up. That selector that I was talking about down there with that metal tape, it tells the elevator where it is. That's where it's hitched to the elevator right there on top. It also has an electrical switch, so if that broke, then an electrical switch is going to open up and it's going to stop the elevator from running because it no longer has feedback on position.
Okay, I don't know where I am now. I'm going to
Right,
shut down.
I'm going to stop. Exactly. So
It looks almost like pipe strap.
yeah, it's pretty flexible. It's really, those have been known to break though because they do have to go around some tight bends.
Yeah.
And they can break.
Now, do you keep track of...
We have everything marked down there on the selector, so if it did break, basically what you have to do is you have to bring the car to a known position, and then you can rewrap it. The bad thing that happens if that breaks, you lose tension on everything down there, and you can actually break pie plates, and a lot of things happen. But that's when you run into problems. But everything's marked. So here's your roller guide system that keeps it inside the rails.
And keeps it from rattling around too
Exactly,
bad.
right. This is where those traveling cables, this is where they come into a box right here. And they actually, they loop down underneath the elevator and up to the elevator, and then they go through this pipe and they go in that ductwork all the way back down to the machine room. They go back to that controller. So whenever somebody pushes a button inside the elevator, it's actually traveling through here and sends the signal back to the controller through that cable.
These cables have AC power for all of this, DC power for the motors, I assume. They have the controls for the elevator. They have the phone line for the e-phone.
Yeah, these they actually had to run a separate one because these cables were old enough they didn't have any.
They didn't have any extra pairs in them.
Right, so they actually ran a separate.
Yeah, I see that. You see the Cat 5 there.
On older ones. Also on older ones, it's very common to see the AC power you're talking about in a separate cable also, because a lot of times that was done from the middle floor on the elevator. They'd bring the 120 in for everything, and then they'd loop it down to the elevator from there. In this particular one, they probably brought it in right here because this is where their main box was.
That wouldn't surprise me.
But you can see that here the counterweights over there too. I don't know how good you can see them, but that's on the other elevator.
Not real well, but
You can see that it's got the same shackle setup. We've replaced these cables on both these elevators within the last 10 years, so.
well, I remember when you guys were here working on them.
Right. So
I've been here 7.
these actually, cables will last 30 years. and sometimes longer. These particular cables actually got wet. There was
Yeah, I saw the
leaks on
old
the
ones.
roof,
They
and
were all
really rusty.
Yeah, I did see.
There's actually a hemp core inside this steel that is actually lubricated when they come out of the factory, and eventually that will dry up. And I keep an eye on them, and I lightly lubricate them. There's a special traction lubrication that it penetrates the cable, but it doesn't
make it so slippery that you don't get any.
You don't get any traction. Exactly. It doesn't compromise the traction. This is
Also
an
something,
example of a guide at the bottom of one of the doors. This is what holds the door from swinging out. It's a guide. You can see the groove down in the sill there. This is you can go ahead.
Oh, I see. So the door doesn't.
Yeah, the door is actually bolted to this side right here, and this
And
lays
that's
down inside the
okay.
sill, and it keeps it in track.
Keeps everything all straight.
Right.
Also, something else in the movies that you see is idiots riding on top of the car.
Right.
I don't recommend that here.
Yeah, you got a low overhead here.
And it's kind of low bridge. I guarantee you, if you were on top of this car when it came all the way up, you wouldn't like it. That's what, from the top of here to the top
You
of
can see the other elevator coming up. You can kind of get an idea
Oh yeah,
how close it is.
there's a foot and a half of clearance there,
Yeah.
if that.
Yeah, it's tiny.
I don't recommend that. And what is this pipe here that I've got my light? The one I got my light on here. This one here.
Okay, that's the guide rail again.
Oh, okay. It looks from this angle. It just looks like a pipe.
Right. Yeah.
And then we've got there's
Cables
what, 3?
going up and down. There's 5.
Oh, okay. There's
That's where they loop down around the driver down there. So one side comes to the car, and the other side goes up and over to the counterweights.
okay.
These
The
cables,
cinder blocks
for a
throwing
5-floor
my.
building, typically cables can be 40 or 50 feet long, maybe a little bit longer.
And
This
it's-
particular one, these cables, I believe, are 220 feet or 250 feet because of the configuration. By putting the machine in the basement, it causes us to have this roping configuration where they loop up and around.
But it's not necessarily a bad thing because
No,
you don't
no.
have any place to put a machine room up
Right,
here.
Exactly. Well, what that forces you to do, anytime you have that up there, yeah, you have to have the extra structure on top of the building. For architects and buildings, it saves them space.
Yeah,
as far as
that,
putting things on the roof.
Although that holds a lot of
It
weight.
does. They still have to have the strength. I mean, that steel beams span across. I mean, they're actually poured into the structure of the building. Those were set.
noticed-
I said the guide rails are the first thing to go in. Actually, when the building's being built, those get set right away. Those beams are set.
I also
when they
noticed
construct
they're
the
at an
hoistway.
angle. Is there a specific reason for that?
Other than just space, probably just it was a way to conserve space. Just because of the governor, if you put that straight across, you get tighter with governor, and it varies. They actually have elevators that have corner post guide rails, just for different space reasons, or the shape of the hoistway, or they have a side exit on the elevator. So the guide rails can actually be on the corners.
Yeah, we have some interesting elevators at the hospital. Particularly the freight elevators.
Oh yeah. I don't know if you Google elevator. I'm sure you can.
Oh, yeah,
get a lot of
I've
stuff.
seen
Elevator
some.
World does a lot of things and talks about how elevators work. There's a lot of hydraulic elevators in Columbia.
We've got one at the VA, and that thing's wicked.
Yeah, that's probably a lot more popular in central Missouri than a geared or a traction actually.
You wouldn't think it would be with having to dig a hole that deep.
Yeah, they're actually, that's the thing from the 60s, 70s, 80s, and 90s, and now companies are starting to go back and they're trying to phase out the hydraulic. They want to get away from the oil, the EPA, and
Yeah, exactly.
putting oil in the ground is a no-no.
Now, something I want to point out for our viewers here, you always see the fans in the top of an elevator. This is why the top of this elevator is just yark, because it's probably not this way everywhere, but I don't see any place for that air to go.
Right.
I don't see any vents out. So it's kind of,
Yeah, you can kind of see. I mean, I vacuumed the other elevator probably a month ago, and you can already see you can see a light dust that car cab's been cleaned.
this one's sitting on 4, and it sounds like they're getting ready to go down. There it goes.
Yep.
Again, that's really cool because that's all electromechanical. There is not a CPU involved in this. Well, that's a quick look at how elevators work. I hope you enjoyed this video. And again, I apologize for the camera work. I know I'm a hack and should get off the internet. Remember to rate, comment, subscribe, and check out thegeekgroup.org where they know what they're doing. Until then, we'll see you.